Hi, everyone, and welcome back to Dave's Math Channel. I'm your host, David Tare, and today I'll discuss how to compute compound interest. So let's begin. So, what is compound interest? There are two types of compound interest: periodically compounded interest and continuously compounded interest. The formula for computing periodically compounded interest involves a geometric sequence, i.e., a sequence of the form t, comma kp, comma k squared p, and so on for some positive numbers p and k, while the formula for computing continuously compounded interest is an exponential function, i.e., a function of the form a of t equals pe to the rt, where t is an arbitrary positive number, p and r positive constants pertaining to the investment, and E is an important mathematical constant known as Euler's constant, or the base of natural logarithms, whose value is approximately 2.71828182885. Euler's constant E is widely considered to be the second most important mathematical constant after pi. Most students don't learn about E until they learn calculus, but it is not necessary to know calculus in this video. Let us first consider periodically compounded interest, which is offered by most banks. There are two important quantities associated with compound interest. The interest rate, denoted as R, is usually given as a percent, and the period, denoted as 1 over n, where n is the number of times at regular intervals of 1 over n years interest is compounded each year. In addition, there are three other important quantities associated with an account that pays periodically compounding interest, namely your principal investment, denoted as P, the length of time of the investment in years, denoted as T, and finally the amount of your investment after T years, denoted as A sub n of T, with P and R as parameters. So given the values of R, N, P, and T, how can we derive a formula for A sub n of T? Before doing so, it is instructive to first consider a simple example. So suppose you invest $1,000 in a bank account that pays 5% interest compounded annually. How much money will you have after 20 years? For this example, we have P equals $1,000, R equals 0.05, N equals 1, and T equals 20. To solve this problem, note that at the end of each year, you will accumulate 5% interest on the total amount of your investment at the beginning of the year, so that after T years, the amount A sub 1 of T of your investment will be 5% more than it was the previous year. In other words, we have equation 1, which says A sub 1 of T is 1.05 times A sub 1 of T minus 1. Equation 1 is an example of a recurrence equation, which you may recognize as the equation of a geometric series. Since your initial investment was equal to your principal, we also have the following initial condition given by equation 2, which says A sub 1 of 0 is $1,000. Together, equations 1 and 2 yield the following solution, which gives the amount of your investment after T years for every non-negative integer T. So this is equation 3 that says A sub 1 of T is $1,000 times 1.05 to the power T. In particular, we have A sub 1 of 20 is 1,000 times 1.05 to the 20th power, which works out to be approximately $2,653.30. So how can we derive a formula for the amount A sub n of t of your investment after t years that can be used for all cases of P, R, N, and T? Note that in this case, after 1 over n years, the amount of interest you will get paid in the next pay period is equal to R over n times the current amount A of t of your account, where t is the number of years since you opened the account. Thus, we have equation 4, which says A sub n of t plus 1 over n is equal to A sub n of t plus R over n times A sub n of t, which is 1 plus R over n times A sub n of t. Another occurrence, which together with our initial condition, given by equation 5, which says A sub n of 0 is equal to P, yields the solution by equation 6. It says A sub n of t is P times 1 plus R over n to the power n times t. So for our second example, suppose you invest $1,000 in a bank account that pays 5% interest compounded quarterly. How much money will you have after 20 years? For this example, we have P is $1,000, R is 0.05, N equals 4, and T equals 20. Plugging these values into equation 6, we obtain A of 4 of 20 is 1,000 times 1 plus 0.05 over 4 to the power 4 times 20, which is 1,000 times 1 plus 80, the 80, and $2,701.48. Finally, suppose you invest $1,000 in a bank account that pays 5% interest compounded monthly. How much money will you have after 20 years? For this example, we have P is 1,000, R equals 0.05, N equals 12, and T equals 20. Plugging these values into equation 6, we obtain A sub 12 of 20 is $1,000 times 1 plus 0.05 over 12 to the power 12 times 20, which is $1,000 plus 1 over 20, 240 to the power 240, which was up to $2,712.64. By now, you may have noticed something interesting. Note that although as expected, the amount of our investment increases as n is increased for some $2,653.30 for n equals 1 to $2,701.48 for n equals 4, and finally $2,712.64 for n equals 12, the amount by which it increases appears to be slowing down. It's A sub n of 20 appears to be approaching a limit as n goes to infinity. In fact, it can be shown that it does. And in fact, this limit is given by the limit of A sub n of 20 as n goes to infinity is 1,000 times the limit of 1 plus 1 over n to the nth power, which is 1,000 times E for $2,718.28, or E, which is approximately 2.71828 is Euler's constant, given by the equation 8, which says E is the limit as n goes to infinity of 1 plus 1 over n to the nth power. So now we'll discuss continuously compounded interest. As in the case of periodically compounded interest, we would like to derive a general formula for the amount A sub C of t of your investment after t years. From equations 6 and 8, we have A sub C of t is equal to the limit as n goes to infinity of A sub n of t, which is the limit as n goes to infinity of p times 1 over r over 1 plus r over n to the nt, which is p times the limit of 1 plus capital N over r to the power capital N over r times rt. So fixing little n for big N is times the limit as little n goes to infinity, 1 plus little n to the our nRT, which is p times the limit of 1 plus 1 over n to the nth, so n goes to infinity, time to the power RT, which is p times e to the RT. Below, we present a table of the amount of your investment. If you invest $1,000 at 5% compounded annually, quarterly, monthly, or continuously after T years, with T ranging from 1 to 20. Note that for each of these cases, continuously compounded interest only results in a few more dollars than monthly compounded interest. Thank you for watching this video. I'll see you next time.